So let's start. And today Lucien Hennecart will give his third lecture in his mini course on Cohomological Hall algebras of two Calabi-Yau categories. So please.
Okay, so thank you very much for making it again today. So I would like to start with a brief summary of yesterday's lecture. So feel free to interrupt at any point, as always, for questions. So yesterday we had some Abelian category, C, sitting in some DG category, D. So the DG category was mainly essential to have like this three-term complex over the stack of objects to be able to construct some virtual pullback. Anyway, so the stack of objects of C, which is MC, fracture MC, sits inside the stack of objects of the DG category D. And we had a bunch of assumptions. So I'm not recording any of these of the assumptions we had, but it's an open substack. And I described some examples. So if you want, just keep one in mind for the rest of this talk, if you prefer. So for example, maybe the most important one is when C is a category of finite dimensional representations of some pre-projective algebra. So pre-projective algebra is some algebra what one can associate to a quiver. I'm not going to recall the definition, but it's a quotient of a path algebra. If you prefer some more geometric examples, you can consider semi-stables, sheaves on some surface, and you want the surface to be symplectic. So for example, case 3 or Abelian. If you're more topological minded, you can take representations like local systems on some Riemann surface. And yeah, we also have this example of multiplicative pre-projective algebras. Okay, so one main feature of all common points of all these examples is the two Calabi-Yau condition. And basically, we want this condition to have local description of the moduli stack MC and of its good moduli space, which I denote by some calligraphic M, by the analogous map for pre-projective algebras. So that's why taking this example, like keeping this example in mind is sufficient for today. Okay, so we have this good moduli space map, which is a map to an algebraic space, which we assume to be a scheme with finite type connected components. And by pushing forward the dualizing sheaf of the stack by this map JH, Jordan-Hölder map, we obtain some object in the constructible derived category of the good moduli space, which we call the sheafified two-dimensional cohomological Hall algebra. So it's understood that we can build a product of this thing, which we did yesterday. So this is an algebra object in this constructible derived category seen as a monoidal category for some monoidal product built using direct submap. Something like this. And also, I explained why this object was concentrated in perverse degrees bigger than or equal to 0. And in particular, if we take the degree 0 perverse cohomology, we get some perverse sheaf on the good moduli space, which has an induced algebra structure. And we call this the sheafified BPS algebra. So this is an associative algebra in the category of perverse sheaves over the good moduli space. Okay. So this part is intrinsic to two-dimensional categories, but I also explain how to recover this sheafified cohomological Hall algebra when C is representations of some pre-projective algebra as some critical cohomological Hall algebra of the triple quiver with a canonical potential. So a three-dimensional construction. Right. So this object lies in the constructible layers category of the good moduli space of the pre-projective algebra, which sits inside the constructible layers category of the good moduli space for the double quiver as a subcategory. And it's not, I wanted to write IQ here. Okay, but if you perform some three-dimensional construction using quiver with potential, there is a formalism providing you with some BPS object associated to quiver with potential. It's a perverse sheaf again on the moduli, good moduli space for triple quiver. And it's a Lie algebra object. So Lie algebra comes from the fact that it was defined using some different perverse filtration starting in degree 1. And this three-dimensional construction provides us with the PBW theorem, which means that some symmetric power of some object, so BPS algebra thickened by equivalent cohomology of the point, is isomorphic to the two-dimensional CoHA of pi q.
Lucien, I have sort of, you see too many algebras, algebraic objects, so it's easy to be lost. So
Yes.
so in two-dimensional case, two-dimensional Calabi-Yau, like for PQ, you have two associative algebras. Yeah, one is a dimensional reduction of this AQ tilde W of three-dimensional CoHA, and another is a BPS algebra. Do I understand correctly?
Yes, maybe I should write some something here to summarize the summary actually. So you have this thing.
And this is a three-dimensional object, yeah.
It's three-dimensional object, and it lives on the good moduli space for the triple quiver Q tilde.
And you can take the dimensional reduction and get two-dimensional. It coincides by some theorem with a two-dimensional CoHA. Yeah.
Yes. So what you do is you forget the additional loops you put on the quiver to build the triple quiver. So this is a map pi. And if you push forward this object, this constructible complex by pi, you get exactly by dimensional reduction this constructible complex defined using the pre-projective algebra.
Okay, great. Also, you have in three dimensions this Lie algebra object, this BPS 3D.
Yes.
I don't know why you wrote it PQ, because it's a bit kind of confusing. It's rather three-dimensional object. All right. And enveloping algebra of this Lie algebra is isomorphic to a sub-algebra, yeah, of APQ. Do I understand correctly?
Yeah, that's correct. So maybe I explain my notation. So in the 3D context, you get this BPS Q tilde W, which is Lie algebra.
Yeah, graded Lie algebra.
And okay, just
it's, yeah, it belongs, yeah, this is better.
and if you push it forward by pi,
Yeah.
it lives in this A pi q, and this is what I denoted BPS pi q 3D. And let's put Lie.
Okay. And
So
this is still Lie algebra, yeah?
It's still a Lie algebra, yes.
And so then you can take its enveloping algebra, and inside of APQ you get some smaller associative algebra.
Right.
Everything is graded many times.
So inside A pi q, we have what I denoted by BPS PyQ algebra, which is a definition intrinsic to two-dimensional. We don't need to pass to 3D. So using some perverse filtration.
All right. So you do not claim any relation between three-dimensional CoHA and this BPS Lie algebra in 3 dimensions. Just one is a subset of another one, Lie subalgebra. Yeah. You do not make any statements.
Maybe I did. So
Okay.
inside, so this BPS Lie algebra sits inside this BPS associative algebra. And in addition, this inclusion identifies BPS algebra with enveloping algebra.
Yeah, this I understand, but it's all about
Okay.
2 dimensions. In 3 dimensions, do you make any statements that your 3D CoHA is something like quantized enveloping algebra of this BPS 3-dimensional thing, or you don't?
I don't make such a statement.
Okay, good. So then in 2 dimensions, you have 2 associative algebras, yeah, like direct image of CoHA and this BPS enveloping algebra, yeah?
Yes.
I certainly know that this direct image of 3D CoHA has many applications, including physics. So then a bit, so why do you need 2 associative algebras? Just in order to identify them with, to have some Kac-Moody up root data and so on, which you do not have for the direct image of CoHA, or why?
So the question is 2 questions. Can we describe this algebra by generators and relations? And can we describe this bigger algebra by generators and relations?
Yes, more or less, yeah.
And we can do it for this BPS algebra, and I will do it today. But describing the full CoHA by generators and relations is a more general question, more complicated question, which is not answered in full generality.
Okay.
Okay. So the plan for today is the following. So I would like to give you some definition of generalized Kac-Moody algebras in the sense of Borcherds. If you know what a semi-simple Lie algebra is, then it's some generalization of this construction. I mean, of the definition by generators and relations. And then I would like to explain to you that the BPS algebra is one of these Kac-Moody algebras, or enveloping algebra of some generalized Kac-Moody algebra. Okay, so I had prepared a slide of motivations for today. I already mentioned part of this. So if you take a quiver with potential, Q is symmetric, which means that it has, so the incidence matrix is symmetric. There is a way to produce a Lie algebra. It's graded by the monoid of dimension vectors for the quiver, and you have a cohomological grading, because everything sits in the cohomology, critical cohomology. So the question, what is this Lie algebra, is a complicated question. And by what is it, I mean, can we describe it by generators and relations? So as I wrote, it's a tough question, and we have very few examples in which we know what this Lie algebra is. So maybe I give you some. If Q is symmetric and you take vanishing potential, then this BPS Lie algebra is Abelian, so Lie bracket vanishes. At the same time, it's interesting, but it's also boring.
So Abelian in graded sense, or what?
Abelian in graded sense, yeah. So it's a super Lie bracket, and everything has to be understood as Z-graded. So yeah. So now I explained to you last time how to construct from a given quiver Q the triple quiver with some canonical potential, cubic canonical potential. And if Q is of finite type, then it was known that this BPS algebra is exactly the positive part of the Kac-Moody algebra, which in this case is actually the semi-simple algebra associated to this to the simply laced Dinkin diagram of a given type.
Who should we which name we should put on this?
So on this, one
Yeah.
name you should put is Davison.
Yeah, this is an obvious choice, but any other names which?
Other names for this,
Yeah,
I don't have any other names for this.
all
But
right.
maybe I should, if you tell me.
No, but I'm asking you because you see there are some results which I thought they should be true long ago, but I don't know who proved them, and this is why
Right.
I'm asking you.
So a proof of this appears in papers of Ben.
In Mainhardt, yeah, probably. No?
I think this one is Ben.
Ben, okay.
Yeah.
Mhm.
And also if Q is affine quiver, which means extended Dinkin, which means Dinkin quiver plus one vertex and connected with one arrow to the finite type quiver, then the BPS algebra is bigger than the positive part of the Kac-Moody algebra associated to the quiver. So you need to add some variable u, and the Lie bracket is linear extension of the Lie bracket on this NQ plus. But in general, we can't say what this Lie algebra is. It's yeah, tough problem. And today, in some sense, we give an answer for any triple quiver with potential. So the procedure is again written here. From a quiver, you can double it by adding an arrow in opposite direction for any existing arrow, and then triple it by adding a loop at each vertex. And for the double quiver, you have pre-projective relation, which is commutator of arrows. And for the triple quiver, you can build the canonical triple potential by multiplying pre-projective relation with the sum of loops, additional loops. Right, and for any such quiver with as many loops as you would like and as many arrows as you would like, we can describe the BPS Lie algebra. But to explain this to you, I need to tell you what the generalized Kac-Moody algebra is, because this Lie algebra will be such positive part of such Lie algebras. Okay, so we start from a monoid, and you may assume that M is n to some power, to Q0, or just some submonoid of this. You have a bilinear form, symmetric bilinear form on M, which you have to think as Euler form of the DG category D. But for now, it's fine. You have a subset of non-zero elements in M, which we call a set of simple positive roots, satisfying some compatibility with the bilinear map. So for any roots, any two roots, then the product is negative if you take two distinct roots, non-positive. And if you take some roots such that the square of this root with respect to the bilinear form is positive, then you want actually the square to be 2. So these conditions are much more restrictive than what you could do to define generalized Kac-Moody algebras. But they are sufficient to describe the BPS algebra we would like to understand. Okay, so we have the set of roots, and for roots, you take G, and G is graded by the set of roots times integers. You add some cohomological grading. It's a It's a vector space with finite dimensional graded pieces, which we call the space of positive Chevalier generators. The graded dual is G check. You can define some Lie algebra using this datum. So the Lie algebra G, depending on all the data I explained, is the Lie algebra generated by G. It's dual, so positive Chevalier generators, negative Chevalier generators, and the Cartan part, which is Q to some power, some Abelian Lie algebra, which I denote by H. They have to satisfy some relations. So it's a bit heavy to get a grasp quickly on this, but let me still explain them. So the Cartan subalgebra is commutative. We can describe the action of the Cartan subalgebra on positive and negative Chevalier generators. So if you make some element of the Cartan commute with some positive or negative Chevalier generators, and you it's an eigenvector, and you have some eigenvalue given by linear form. If you make some positive and negative Chevalier generators commute, then it's most of the time 0, except when I equals j, and then it's a multiple of some Cartan element. And last, you have the Serre relations, which means that some iterated brackets of some Chevalier generator, and iterated means that we apply it this number of times, 1 minus hi hj, to some over 1 is 0 under some conditions. So if hi, the pairing of hi with itself is 2, or if hi and hj commute, so which means that the pairing is 0. So yeah, so if I is a root, I think it's written on the next slide, but if I is a root, it's inside this monoid, and then I use the notation hi to denote this element seen in this vector space, which is by definition H. Okay, so the upshot is that we have some Lie algebra defined by generators and relations.
So I guess I want to have a quick understanding of this 5 plus. So 5 plus is kind of mimicking the simple roots in the Kac-Moody Lie algebra case, or all positive roots. Or I mean
Yes, it's simple positive roots of the Kac-Moody algebra.
okay, thank you.
I have examples on the next slide or the one after, and you will see what you get, how to recover Kac-Moody algebras using this construction. But first, some general things. So we have a triangular decomposition as for Kac-Moody algebras. So we have in the middle Cartan part, the subalgebra generated by G, the space of Chevalier generator is n plus, and the subalgebra generated by G check is n minus, and we have this direct sum of vector spaces. We have trichotomy of roots. So the roots hi for I in the set of roots can be real, what we call real, if the pairing is 2. We have imaginary roots when the pairing is 0, and hyperbolic roots when the pairing is negative. Okay, for usual Kac-Moody algebras, we would only have real roots. In here, we have some 2 more families.
So it's a Borcherds type of Lie algebra.
It's sorry, I couldn't hear.
Borcherds Lie algebra.
It's a Borcherds Lie algebra. Yeah, exactly. Right, and the positive part n plus is generated by G with satisfying only the Serre relations. Okay, so the positive part itself has a description by generators and relations. Right, so let's move on to some examples to have a better feeling. So we start from a quiver with vertices Q0 and arrows Q1. the Cartan part is given by q to the power q0. We have the symmetrized Euler pairing on this vector space H, which is given by this formula. So some formula, yeah, regular classical formula. First example is when Q has no loops, the set of positive roots is exactly the set of vertices of the quiver, which you embed inside the monoid by taking the corresponding basis vector. And for any root, for any vertex of the quiver, you take one-dimensional generating subspace, which is Q. Then the construction I explained using this monoid with the symmetrized Euler pairing gives you the Kac-Moody algebra associated to Q by Katz and Moody. The example 1.5 is when you take a bigger set of roots. So the set of roots is Q0 real. So real vertices are the vertices which don't carry any loops. And Q0 imaginary, but you have infinitely many roots for any imaginary vertex. And you embed this inside n to the Q0. So again, for each root, you take one-dimensional generating subspace, and then the Kac-Moody algebra you get, the generalized Kac-Moody algebra you get, is the one associated by Bozek to a quiver in his PhD thesis. So it's the correct generalization to quiver with loops of the Kac-Moody you associate to a quiver. And the last example is more, is really non-Kac-Moody example. It's really Borcherds, like generalized Kac-Moody example. When you take the quiver with one loop and one vertex, the set of roots is the set of positive integers inside the Cartan, which is one-dimensional. And for each integer, for each positive integer, you take a one-dimensional space, but situated in some cohomological, non-zero cohomological degree. So this vector space has to be z-graded. In previous examples, it was like sitting in degree 0, but in here we put it in degree -2. And what you obtain is the Heisenberg-Lie algebra acting on the cohomology of the Hilbert scheme of points on the plane.
So I missed why we obtained from this description that it acts on the cohomology of Hilbert scheme.
So directly from this description, we don't obtain this, but what I wanted to say is that this is the Lie algebra considered by Nakajima in his work on Hilbert schemes of points on the plane.
Yeah, okay.
Okay, and yeah, so this algebra appear naturally from geometry, as I will show today. And also they act on many important moduli spaces, as I might explain tomorrow in the applications. But I explained to you that we define BPS algebra in some monoidal category of perverse sheaves. So we would like to upgrade this construction of Kac-Moody, generalized Kac-Moody algebra in such monoidal categories. And actually it's quite straightforward if we only restrict to the positive part. Okay, so we take a monoid in schemes as usual, and we assume that the monoid of connected component is something we understand well, which is a submonoid of this n to some power, where Q0 is finite. And we take, instead of a generating vector space, we take a generating perverse sheaf. So for any positive root, we take some perverse sheaf GD. on the corresponding connected component of the monoid M. So we assume that there is some map is a finite morphism, so that it preserves perversity. And additional assumptions are the following. So the connected component of the monoid M corresponding to a real root, so D is 2, has to be a point, and the generating perverse sheaf, when D is a real root, has to be the constant sheaf concentrated on this point. And then what we do is that we define the N plus as the Lie algebra object in the category of perverse sheaves over the monoid M, generated by G, modulo the Serre ideal. And the Serre ideal, so you have it is generated as a Lie ideal by the Serre relations. So the adjoint action of GD on GD prime, if D and D prime their pairing is 0, and the adjoint action of GD applied some number of times to GD prime is 0 when D is a real root.
Is it possible to add the Cartan to this strictly positive part of in perverse setting?
It may be possible. I haven't thought precisely. What is not possible is to also add the negative part.
Yeah, this is clear, but
Yeah.
adding Cartan, it's always a bit artificial thing, but if you could, then I would ask you what's analog of the Weil group, because I don't see.
What's the analog of?
Weil group. Weil group.
Yes.
Your Weil group.
Yeah.
While it depends. You see, I would like to distinguish between two Weils.
Yeah, Agreve or
Yeah,
Hermann.
I'm talking about Hermann, so that's somehow
I see.
Yeah, I have. I think I went in Göttingen some years in the past, and I think Hermann Weil was in Göttingen in the
So it should be
19th or 20th century.
Yeah,
And I saw his house, the house he was living in.
Okay, great. Now the question about the group which he invented in a special case and was generalized later by other people, which is noted by W in honor of him.
Yes. So I think a Weil group question is a great question. And so Weil group is defined using the reflections at real vertices, so vertices carrying no loops.
Yeah, but
so the reflections about generated by simple roots.
Yeah, but it does not preserve positive roots.
It doesn't preserve positive roots. And yeah, I am trying to understand this because this Weil group should act in some appropriate sense. I mean, it acts on
in the quiver case, there is an interpretation of this by BGP reflection functor.
Yeah, BGP, we can define BGP for projective algebras. We can make things work in terms of cohomological Hall algebras.
You see, if you work with spherical generators instead of simples, as you do, then in the category you do have a spherical reflection in the object, and so you have a subgroup in the group, let me call it group autoequivalences of your category, and so generated by these reflections. So then actually probably maybe Rina can comment on that. So, yeah, all right. So anyway, there is no Cartan, so that's
yeah, so for now there is no Cartan. Yeah. Okay, so by Lie algebra generated, I mean you take the free Lie algebra generated by G, and you quotient out by the ideal generated in this category, monoidal category, by these relations. So this is a construction that works quite well.
So the monoidal category is the perverse
And
F is the monoidal category you are talking about.
yeah, it's monoidal
And
category
also
with this.
pervert is up to degree shifting, right? So you have the Z grading that's given by the
In this case, I mean, you obtain the Z grading, sorry, when you take derived global sections and you take cohomology of perverse sheaves, so you have a graded vector space.
Okay.
But in the realm of perverse sheaves, we don't have this Z grading directly. It's an actual perverse sheaf.
So actually, just actual, not up to gradation. Okay.
Yeah.
Thank you.
Okay. So now we come to the most important part of this series of talks, which is the description of the BPS algebra by generators and relations. So I have to tell you what the set of roots is for some given some abelian category C. And then I have to tell you what the generators are. I have to tell you what the monoid you take and what bilinear form on this monoid. Okay, so let's start from the beginning and define some set sigma C, which is the set of connected components of the good moduli space having a non-empty locus of simple objects, which means that the Jordan-Holder map, so automorphism group of a simple object is GM, multiplicative group. So this condition is equivalent to saying that Jordan-Holder map over this, the corresponding connected component, is a GM job. So once we have this set sigma C, we define the set of positive simple roots by taking the union of sigma C with the set of all multiples of elements in sigma C which are isotropic roots. So isotropic roots behave in some particular way. We need to take all multiples of them. Okay, so this is the set of simple positive roots sitting inside the monoid of connected components of the good moduli space, on which we have the bilinear form given by the Euler form of the DG category D. So it's given by alternated sum of homomorphism between objects in the triangulated category, which is the homotopic category of T. If you remember a little bit, I gave you some conditions the positive roots, the roots had to satisfy, which is having a negative pairing. So two different roots have a negative pairing and blah, blah, blah. This is a fact that this is true in this situation. Okay, we have the set of roots. Now, how to define generators? So for any root, we have a generating perverse sheaf on the corresponding component of the good moduli space. And what is this perverse sheaf? When A is in this subset sigma C, we take the IC complex of the good moduli space. So some perverse sheaf given by intermediate extension of the constant sheaf on the regular locus. When we take a root which is a multiple of some element of sigma C, we have to do something a bit different. So we consider the diagonal map from the good moduli space to taking an object to the elf power, elf direct sum of this object. So you multiply the dimension here by L. And then what you take when A is in sigma C, an isotropic root, and L is a multiple, L is an integer. You take the push forward by this diagonal map of the IC complex on this good moduli space. So in some sense, this is a perverse sheaf on this connected component supported on the small diagonal. So now we have the roots, we have the generators, and so we have everything to construct some Lie algebra in the category of perverse sheaves over the good moduli space MC. So we have to make sure that we have maps from this generator object to the BPS algebra itself. So this is the object of this proposition, telling you that for any root, we have a canonical monomorphism from the generator GA to the BPS algebra. Because if you take the zero map, then okay, it's a map, but it's not going to help you very much. I've included a proof. So when A is in sigma C, it's quite obvious what you have to do. You use the fact that the JH Jordan-Holder map, good moduli space map, is a gem job by definition of sigma C. And then, yeah, I don't want to bother you with this because it's a calculation you can make. The simple locus is smooth. And then the restriction of the sheafified cohomological Hall algebra to the simple locus is actually given by the constant sheaf on the simple locus shifted. So this thing is a perverse sheaf with the C-star equivalent cohomology of the points. So this thing is a sub-object, and then you use semi-simplicity of the sheafified cohomological Hall algebra, which allows you to find the map, the monomorphism from JA to the P. So this sorts out the case of non-isotropic roots.
So you don't need kind of decomposition theorem here.
We need for semi-simplicity. So we know that AC is semi-simple by decomposition theorem for like the special decomposition theorem for two Calabi-Yau categories.
You don't need that this BPS is a direct sum of something so far. You need just embedding. Okay.
Yes.
And also the classical decomposition. So some kind of smoothness in the modular space case. Do you need those conditions? Especially when you look at the constant shift by shifting, and so that's a perverse sheaf.
Yeah. So in here I use that the simple locus, where the JH map is a GM job is smooth.
Okay.
But if it were not smooth, I could always restrict to smaller locus.
I see.
Smooth locus.
Okay. Thank you.
Right. And when we have anisotropic roots, then we define some push forward by diagonal map of some IC complex. And we also want some monomorphism like this. It's trickier. It's trickier to exhibit, but it's possible. It's isotropic behavior. So everything behaves like Jordan quiver, so triple Jordan quiver with a canonical cubic potential. And yeah, maybe let's skip this because it's a bit technical and it's not very enlightening. But now we have all the ingredients to state the theorem A, which is description by generators and relations of the BPS associative algebra associated to the two Calabi-Yau category C. It is exactly given by enveloping algebra of positive part of the generalized Kac-Moody algebra generated by this object. So this is JA. And as always, I distinguish the cases when A is in sigma C or when A is isotropic, like this. Oops. My app closed. Yeah, it happens sometimes. So I need to go to the theorem. Here we go. Right. And the bilinear form is given by the Euler form. Euler form, it's real Euler form of the DG category. Okay. And so in particular, because this Lie algebra, which was pushed forward from the three-dimensional situation, is the positive part of the generalized Kac-Moody Lie algebra. And so this gives a description of the BPS algebra of triple quiver with potential. Well, everything is in categories of perverse sheaves, but if you push everything down to the point, it's a monoidal functor, as I tried to explain in the first lecture. And so everything you can prove over in perverse sheaves, you obtain the similar statement for vector spaces and cohomology.
Can I quickly ask you about the Euler form? In the Abelian case, Euler form can be described in terms of the extensions, x to i's. So in the DG case, what?
So if the category C happens, how to say? This is what it is, but we want it's taking the Euler form with respect to D is to take care of some generated cases. And the generated cases, I mean, for example, when C is representations of pi q,
Yeah.
when pi q is not two Calabi-Yau category, two Calabi-Yau algebra. For example, if q is a point, then pi q is homological dimension 0 algebra.
So
And so this is not.
Yeah, this is not an X algebra this time.
No,
It's not defined by X.
X for which category? There is no quiver here. There is pre-projective algebra from the very beginning.
Well,
So
for Abelian category, one can do that.
but then you have to symmetrize. So when you go to
Well, if you have one, you can symmetrize it. But
yeah, but he doesn't. So that's
he doesn't. He just say in the DG category, you have a way to define this.
no, it's not about DG. It's about two Calabi-Yau.
Okay.
So, okay.
Okay. Yeah. So that's coming from two Calabi-Yau condition. Thank you.
Yes. Thanks. Okay, so the right bilinear form to take is this one. And second theorem is PBW theorem. So we are in the same context of two Calabi-Yau Abelian category C. This Lie algebra is the one that appears in the theorem A, the GKM. Then we can construct a map from the symmetric power of this Lie algebra tensor C star equivalent cohomology of the point to the sheavified cohomological Hall algebra. And this is an isomorphism. So when C is category of representations of some pre-projective algebra of some quiver, this follows directly from dimensional reduction and the PBW theorem for quivers with potentials. But when C is an arbitrary two Calabi-Yau category, this is an actual theorem. And it follows basically from local neighborhood theorem for two Calabi-Yau category and compatibility of multiplications. Okay, so in the remaining 10 minutes, I can give you a very brief overview of how to prove these theorems. So the idea is very nice. I encourage you to continue listening a little bit. So I explained that we have canonical maps from the generators to the BPS algebra, associative version. When you have map from sub-objects, you can naturally extend it to a map from the free algebra generated by the direct sum of all these objects to the BPS algebra by just using multiplication, as in the category of vector spaces. And inside this free tensor algebra, there is the Serre ideal generated by Serre relations. So we had the adjoint action of something applied a certain number of times to something else was 0. So we would like first to prove that phi vanishes on the Serre ideal. Vanishing on the Serre ideal so that you can deduce a map from the quotient. And now you want to prove that this map is an isomorphism, because this thing is exactly enveloping algebra of what I denoted NC+. And both sides are semi-simple perverse sheaves. This side, it's a theorem, and this side is semi-simple by construction. So it's a morphism between semi-simple perverse sheaves. If you want to see that it's an isomorphism, you can look at the kernel and the co-kernel, and you want to prove that both vanish. And for this, you can reduce to pre-projective algebras of quivers. I didn't say why, but you can do it. And then what you need to do is to prove the result for pre-projective algebras of quivers, which you do by induction. So let's say if phi pi q is not an isomorphism, then the kernel or the co-kernel of phi pi q doesn't vanish. So it's a semi-simple perverse sheaf, and it's non-zero. So you may pick a point in some connected component of the good moduli space for which the restriction of this kernel plus co-kernel is not 0. You can just take a point in the support, semi-simple perverse sheaf is given by local systems, so you can find such a point. Then this element X gives you a semi-simple object in the category C, so you can write it as a direct sum of simples. And what you get is a collection of simple objects. So you construct the X quiver for this collection of simple objects. You take the pre-projective algebra, blah, blah, blah. And there is a way to deduce that the corresponding morphism phi pi QS for the quiver QS is not an isomorphism. And so we moved to another quiver. And so on and so on. We can iterate this induction. So, and at some points.
So I missed the iteration point. So you get collection of simples, you get kind of a different quiver, which is just for this collection, and then what?
And then you use a local neighborhood theorem.
Okay, all right.
To see that this map, the corresponding map phi pi QS. So this map, but for the quiver, for the pre-projective algebra pi QS, is not itself an isomorphism. So we moved from one quiver to one over. And the key of this induction procedure is the following. So I explain you the key. If you have a quiver with pi q pre-projective algebra, some elements in the good moduli space, which corresponds to semi-simple representation of pi q. We denote by D the dimension of the semi-simple representation. And we take S underline S, the collection of simple objects, simple representations of pi q, which we obtain this way. We let Q bar S be the X quiver of this collection of simple objects. And Mi is a dimension vector for this X quiver. Then what we can prove is that the new quiver with the new dimension vector is smaller than the original quiver with the original dimension vector, D, for some total order on the set of pairs of a quiver and the dimension vector, whose support is the whole of the quiver. And this partial order is defined as follows. So QD is smaller than Q prime D prime if total dimension of D is smaller than total dimension of D prime or we have equality of total dimensions, but the number of vertices of the quiver Q is bigger than the number of vertices of Q0 prime. So we do an induction on this set of pairs of quiver with dimension vectors. And then at some point, we can't do induction anymore. We can't iterate. I mean, what we produce is going to produce, the X quiver is going to be the same as the quiver we started with. And this case is dealt with using strictly semi-nilpotent cohomological Hall algebra.
What is it?
Which is something I will explain tomorrow. But so I have time to tell you what it is. It's so instead of the stack of representations of pi q, you take the substack of strictly semi-nilpotent representations.
What is semi-nilpotent?
Which means that you take representations of pi q.
Each 1/2 of arrows is nilpotent.
And yes, but it's a stronger condition actually.
So you have, yeah, the composition, you should include paths, not only individual. Yeah, okay.
Yeah. So you have a filtration of M by sub-objects, M1, M2, MR, which is 0, and the subquotient is concentrated at one vertex.
Mm-hmm.
And semi-nilpotent means that the action of the original loops send Mi to Mi plus 1, but the action of the opposite loops preserves the flag in a large sense.
I'm trying to make, but maybe it's a question to the end of your talk. I mean, this PQ is certainly algebraic analog of a category of Higgs bundles. And
Yes.
so, like, I think in Lustig's story, maybe Zongzhu remembers better, he has an analog of the nilpotent cone, for which is not as thing that you defined by something weaker. And I'm trying to see what's the geometric analog of this semi-nilpotent story.
It would be a global nilpotent cone.
Global nilpotent cone, what you it's an analog of what you're saying, yeah?
Is analog of what I'm saying.
Oh,
The thing
right.
is that Lustig works with quivers without loops. And so Lustig takes lambda G, which is nilpotent representation of pi q of dimension D. But when you have loops, taking nilpotent representations is not good. But you need to take semi-nilpotent. So this thing is Lagrangian when Q doesn't have loop.
Yeah, and your semi-nilpotent will be also...
It's stronger than your potent.
and your semi-nilpotent will be also Lagrangian.
This semi-nilpotent, yes, semi-nilpotent is Lagrangian without conditions on Q, but nilpotent is not going to be Lagrangian.
Mm-hmm.
So when the quiver has loops, then Lustig's definition differs from semi-nilpotent definition, and it gives something less well-behaved. But I can come back tomorrow because this is what I plan to explain. So this is all for theorem A, I wanted to say. And for theorem B, you proceed in a very similar way, but actually it's much simpler. So if you stop listening, you can start again. And first, what we want to construct is a map from symmetric power to sheavified cohomological Hall algebra, which we do as follow. So the BPS Lie algebra sits by definition inside the BPS associative algebra, which we show in theorem A was the enveloping algebra of this thing. And we had a canonical map to the whole sheavified CoHA, which was an adjunction map for some truncation functors, perverse truncation functors. Now, the sheavified cohomological Hall algebra has an action of the C-star equivalent cohomology of the point, which is an algebra isomorphic to polynomial algebra in one variable. This is the action, so the generator U acts by multiplication by the first Chern class of the determinant line bundle. The determinant line bundle on the stack of objects in C. So if you combine this inclusion with this action, you get a map from the tensor product of the Lie algebra and the C-star equivalent cohomology of the point to the sheavified cohomological Hall algebra. Then you can naturally extend this map to the symmetric power using first the embedding of symmetric power inside the free tensor algebra of this object, and then using the canonical map given by CoHA multiplication to the sheavified cohomological Hall algebra. Once you have this map, phi C, the PBW theorem tells you that this map is an isomorphism. And what it suffices to show is that for any point in the good moduli space, the Schrick restriction of this map phi C to this point is an isomorphism. Otherwise, you take the cone of this morphism in the constructible derived category. I mean, what you want to show is that the cone is 0. And this is implied by these conditions for any point x. And again, such a x corresponds to a semi-simple object of C. So you take the collection of simple summons of this semi-simple object, and you take the x quiver for this collection of simple objects. You have some embeddings of this monoid NQ0 inside the stack of representations of preprojective algebra of Q. So some M is sent to the 0 representation of dimension M. And on the other side, it's sent to the direct sum of Si to the power Mi. And by local neighborhood theorem, the Schrick restriction of phi C is exactly the same thing as the Schrick restriction of phi pi q using these maps. And so, because we know that this thing is an isomorphism, because we know that PBW theorem is true for preprojective algebras of quivers by dimensional reduction, we deduce that higher power Schrick of phi C is an isomorphism. And so we deduce the PBW theorem for any two Calabi-Yau Abelian category. And this is all what I wanted to say today.
Okay, thank you. Are there any questions? Okay, so if there are no questions, so let's wait for the last lecture tomorrow.
So tomorrow is the most entertaining one with applications and something light.
Okay. And then maybe may I ask you sort of a bit perpendicular question? So it's probably the structure theorems kind of they are all over. There is also a notion of a constructible Hall algebra, yeah, which can be defined well in a similar circumstances, yeah, even maybe a little bit more general because you do not need the Artin stack, but it's enough to have constructible stack. But anyway, more or less the same. So, and there was a kind of a puzzle, maybe still a puzzle, about the relation between Coha and this constructible, more conventional whole algebra, yeah, because in the end they give the same invariants. So not at the level of algebras, but at the level of Donaldson-Thomas invariants, answers agree. So my question is there any relation at the level of algebras?
Yes.
Yes.
Yes,
Okay.
but yes.
What is it?
So constructible whole algebra of the quiver Q, okay, over a finite field FQ is something which is isomorphic to quantized enveloping algebras.
Yes.
Of some Lie algebra.
Yes.
And well, this is almost the same Lie algebra as we have here for C equals pi Q.
Yeah, but it's kind of you should prove some difficult theorems in order to compare. But my question is at the level of definitions, like, you take direct image, say, for example, constant sheaf, so you work with cohomology. This is why it's cohomological, yeah.
Yes.
And if you are of a finite field, so there is a relation between cohomology over, I don't know, over, say, complex numbers and Eliadic cohomology active Frobenius. So you can, in the end, recover some parts of cohomology working over finite fields. So then my question is rather a definition similar to what you described for CoHAs and similar theorems, kind of, but for constructible whole algebra. We did something with Maxim long ago, but kind of I was not very satisfied with this. Not derived, but some kind of derived whole algebra. Again, it's only 1/2 of the real of the full thing. Yeah.
Yeah, before we answer your question, I'm a bit of a puzzled, but your CoHA, when you're taking cohomology, you are really taking the equivalent cohomology. That is
So it's
quite
cohomology
different from
of
simply taking cohomology.
No, it's cohomology of a stack. If a stack is a quotient,
Okay.
then it's the same. There is
That part is going to be, I was planning to ask the question tomorrow because I missed the first talk. It looks that you are taking the perverse shifts on stacks or modular spaces.
no.
It is-
If I understand, okay, so it's a good, possibility to check understanding. It's my understanding that there is no good theory of perverse sheaves on stacks, and this is why he applied this Jordan-Holder map to the coarse moduli space. Am I
Okay.
right, Lucien?
So
not?
what I would say is you can't define a multiplication directly on perverse sheaves on the stack. Because I had the diagram in previous lecture. Maybe if you allow me to go back to M seminar number 2. So I tell you when I found the diagram in a few. This one, yeah. This diagram commutes because you put the direction here, and the going to the coarse moduli space kills extensions. So this is why it commutes. So you take an extension, but you go here. It's semi-simplification, right?
Yeah, so the upper part is the upper line stacks, and the lower part are coarse moduli spaces of this diagram.
Yes, but if you put only the stack here, I mean, if you relate the stack by the direct sum to MC, it's not going to commute. So I put it in red so that if you put direct sum here from yeah, it's not commuting. Like the first
So
row
you
and
need to use both. Okay. With the assumption that something, this P is proper and the other one is quasi-smooth. These are assumptions in general.
yeah. But you can do
So
perversions
in
and
this
stack.
picture here, can I interrupt? In this picture, just shown from that stack on the top, you have. So when you take the cohomology, as Ian mentioned, as a stack, but in the constructible sense, I guess in the constructible sense, what does the perverse sheaf or on the top mean? This is probably what Lustig in the quiver case worked very hard to try to.
Yeah, so for quivers, Lustig was considering maybe this is an answer to Jan's previous question about. So the constructible Hall algebra of quiver Q over FQ. Lustig was inspired to define some category of perverse sheaves on the stack of representations of MQ. To categorize the positive part of the quantum group, define canonical bases and and if you take
actually what Lustig didn't work over finite field. Lustig was working over the algebraic closure of the finite field.
Yeah, so
using the L-adic cohomology, I would say.
Right, and you can do his construction over C, actually. So this is complex stack of complex representations. And there is some pi Q, it's inside perverse sheaves. So Lustig's category. And this stack is a smooth stack because Q is smooth. Path algebra is a formally smooth algebra. Inside, and it's even bounded. And so you can take the K0. I mean, this category is semi-simple, so it's generated as a and there is something called characteristic cycle map, so a tool from microlocal geometry, and it gives you a Lagrangian cycle on the cotangent stack to MQ, which is cotangent stack is a stack of pi q, stack of representations of pre-projective algebra. And Lagrangian cycles, well, you can say more in this situation is that you land for quivers with loops inside the stack of strictly semi-nilpotent representations. So you land inside this stack. And this stack is Lagrangian. So characteristic cycle of Lustig perverse sheaves is going to be a Z-linear combination of irreducible components of this stack of strictly semi-stables. And this thing sits inside the cohomological Hall algebra, so constructed using Borel-Moore homology of the stack of strictly semi-nilpotent. And it happens to be stable under CoHA product. So you actually have on this subspace of Lagrangian cycles of this stack, you have a CoHA product induced. And what is true is that the characteristic cycle map is an algebra morphism. So you can relate Lustig construction to some small part of the cohomological Hall algebra.
I see.
Okay, great. All right. Okay. So any more questions? Well, if not, thank you, Lucien, and we'll see you tomorrow, and tomorrow it will be 1:30 p.m. Yeah.
So please come because it will be more entertaining.
Okay.
Okay.
Yes.
Well,
Okay.
thank you very much.
No
Appreciate it.
problem, no problem. Okay, thank you and have a good day.